Hello again. Now we're going to start on an actual example of doing a proof involving sets. Pretty much the most basic thing that you might want to do that gets complicated here is prove that two sets are equal. So if you'd like to prove that two sets are actually the same set, what you need to do is you need to show that they contain the same elements. And if they could be infinitely large, you can't just go through one element at a time. So what you want to do most of the time is you want to show that if an element is over here, then it's also over here. Seems simple enough, so we'll take a general element of this one and prove that it's an element of this one. That shows me that everything here is here, but I need to go the other way as well. So this is sort of an if and only if. When I'm showing that two sets are equal, it's a lot like showing that two definitions are equal. I want to say that everything over here is over here, and everything over here is over here, and that means that they share an exact same set of elements. So for an example, let's look at two sets that we already feel pretty confident are equal. We'll look at the set of all things that are divisible by 3 and the set of all things that are divisible by -3. So I want to show, as my claim, x such that 3 divides x is equal to x such that -3 divides x. And so I'm going to start by taking something from the set where 3 divides x. And I'm feeling a little bit lazy right now. So before I do that, I'm going to give that set a name so that I don't have to write the set of all x where 3 divides x every single time I want to talk about it. So I'll start by saying let A be the set of all x where 3 divides x, and I'll let B be the set of all x where -3 divides x. Now we're going to want to take something from A and show it's in B, and take something from B and show it's in A. Just like an if and only if proof, it's a good idea to separate these into two paragraphs whenever you're doing it, even if they turn out to be very short paragraphs, as will probably be the case this time. So I'm going to take little a, element of big A. It's sort of a faux pas to use x. We'll do it sometimes, but if x is your dummy variable, you don't really want x to also be the random variable that you select out of the set A, because it's sort of like we already have a meaning for x, even though we don't. It's just a placeholder, but we'd like it to be able to maintain its placeholder quality. And I don't want to use this definition, where am I? I don't want to use this definition later if I've already told you that x is one specific value. So we don't want to fix f if x is also being allowed to vary and also being allowed to take different values within the set. So I have little a in big A. That only tells me one thing. Therefore, 3 divides little a. And there are a couple different tricks that we can use here. I'm just going to go with the definition, because we can, and definitions are easy. Since 3 divides little a, that means that there's something times 3 that gives us a. So there exists b in the integers, I knew this was going to happen. My pen's getting angry from writing on the wall. Such that 3b equals a. And then this is pretty easy. I just need to show that -3 times something equals a. What Do I multiply negative 3 by to get A? Well, I multiplied positive 3 by positive B. I'll multiply negative 3 by negative B. So negative 3 times negative B equals A. And since B is an integer, negative B is an integer, therefore negative 3 divides A. Since negative 3 divides A, we now know that A is actually an element of B. And so what we've shown here is that everything in A is also in B. We took one random element from A, could have been anything, and we showed that it was in B. So that means that every element of A is going to turn out to be in B. To go the other way, I'm going to let little b be in big B. That means only one thing. Negative 3 divides little b. And so I know that there is something that I can multiply by little b, multiply by negative 3 in order to get little b. So there is an a in the integers such that negative 3a is equal to b. And then we're going to use the same logic. 3 times negative a is equal to little b. And negative a is in the integers. So 3 divides little b, and we can say that little b is in the set A. So we've shown that everything in B is in A and everything in A is in B, and so therefore they must actually be the same set. We denote this relationship where everything is in B is in A by saying that B is a subset of A. So we've shown up here that A is a subset of B, and we've shown down here that B is a subset of A, and since A is a subset of B and B is a subset of A, they're the same set. So this subset relationship, we have special notation for it, and the notation here can get a little bit confusing. We say A is a subset of B to mean everything in A is in B, exactly what we just showed above. And we denote it with this elongated C. Don't use an actual C shape. It's an elongated C. It's certainly different looking than a C symbol. We use this to denote subset, and then sometimes we use a deceptively different looking symbol to denote subset. So this can be achieved with this symbol, a regular elongated C, or an elongated C with a line under it. This seems in parallel with the less than symbol and the less than or equal to symbol, and I wish at the pit of my being that they actually were, and that mathematicians worldwide could agree that this symbol means is a subset or equal, and this symbol meant is a subset but is not equal to, in the exact same way that less than and less than or equal to are different, but they're not. This isn't how we differentiate those two symbols. Both of them mean subsets that could be equal. You'll definitely find books that will use that logical way of defining them, but those books will have to tell you that that's what they're doing at the beginning of the book, because this is not standard notation. Standard notation is that those two symbols mean the exact same thing, subset or equal. If we want to specifically rule out the possibility of equality, if we want what's called a strict subset, where A is in B and they're not equal, we have a special symbol for that. Now, it's not the case that you always have to use this symbol for subsets that are not equal to their superset. It's just that if you specifically want to state that it's impossible for them to be the same set, then you need to use this symbol because that's what it means. The symbol is a subset symbol with an equal sign underneath, a full equal sign that's been crossed out. All right, and on tech, the subset symbol is \subset, and the subset symbol to state that they are not equal, the strict subset symbol, is n subset EQ. An n at the beginning of a tech code, of a specific \something in tech, often means that we're making it not the case, often means that we're putting a slash mark through it to denote that it's not happening, and that's what it means here. Alright, so I think we're going to, actually, I'll give you one more tech thing, and then I'll take another break, and then do one more video to do one or two more examples. The last thing that I want to give you is if you want these things to go the other way, if you want to say something is a superset of something, meaning that it's the set that contains it, if you want the C symbol to go the opposite direction, it's supset instead of subset. So S-U-P-S-E-T. All right, see you in a minute.